Welcome everyone. Today is our last lesson of Unit 1 of vectors, and it has some applications that involve resolving a vector into rectangular components. So when we say the word resolved, any vector, any single force vector can be resolved or split into two vector components which add to give us that single vector. Now this can be technically done in an infinite number of ways. If we imagine a vector here, I could split this like this, or I could split it like this. I can split this into kind of an infinite amount of parallelograms that can be used to create that single vector. Now, the most useful and important way that we can kind of resolve a single force or a single vector is when it's resolved into two components, which are called rectangular vector components, also referred to as horizontal or vertical components of the vector. All right, so one kind of helpful thing here is when we resolve a particular force or vector into its rectangular components, we can kind of, sometimes these are called fx and fy, or force horizontal and force vertical, depending on what type of question we're working with. But if we use SOHCAHTOA here, here's the idea. If theta is the angle that the force makes with the x-axis, we could consider this to be adjacent, opposite, and hypotenuse. So what I do know is that if I'm looking for the force of x, I need to use adjacent and hypotenuse because we would assume that we already know the force. We're just trying to find the x component of that force, and I would use cosine. So I would say the cos of theta would be equal to adjacent, which would be the magnitude of the force in the x direction, over the magnitude of the force, which is the hypotenuse. So if I multiply this magnitude of my force up, I get that f at x will be equal to the magnitude of the force itself times the cos of theta. Okay, similarly, if I'm looking for the y component or the vertical component of the force, I need to use sine because I have opposite and I have hypotenuse. So if I set up sine of theta, this is going to be equal to the magnitude of the vertical part of the force over the magnitude of the force. Now, if we multiply this magnitude of the force up, we're going to get that the y component or vertical component of the force is equal to the magnitude of the force itself times the sine of theta. Okay, you can square these or highlight these because we're going to kind of do this instead of trying to isolate for these forces every single time. Okay, so let's take a look at a couple examples. Today's lesson is going to be relatively quick. A tow truck is pulling a car from a ditch. The tension in the cable is 15,000 newtons at an angle of 40 degrees to the horizontal. Draw a diagram showing the resolution of the force into its rectangular vector components. Determine the magnitudes of the horizontal and vertical components of the force. Okay. So here's our force. It is tension, and it's 15,000 newtons. And then I'm going to have a force that is horizontal and a force that's vertical if I separate these guys out into their components. So perhaps we would label this tension in the x direction or even tension in the horizontal direction versus tension in the vertical direction. Okay, it doesn't really matter what you call these. If it's helpful for you, you can keep it as x and y, but you may see a variety of things used if you look at other sources. So let's just say y for our sake. And we know that to the horizontal, this angle is 40 degrees. So there's our diagram. Part B asks us to find those horizontal and vertical components. So I'm just going to use those formulas that we developed up in the above example. And I know that the tension in the x direction is going to be equal to the magnitude of the tension times the cosine of the angle, whereas the tension in the y direction or the vertical direction is going to be equal to the tension times the sine of the angle. So I do know that the magnitude of the tension is 15,000 newtons. So I'm simply going to multiply 15,000 newtons by the cos of 40. And similarly for the vertical component, we're going to multiply 15,000 newtons times the sine of 40. So we'll enter these into our calculator quickly. And you should get values, let's say approximately equal to 11,490.7 newtons for your horizontal force. And for your vertical force, you should end up with approximately 9,641.8 newtons. Kayla pulls on a rope attached to her sleigh with a force of 200 newtons. If the rope makes an angle of 20 degrees with the horizontal, determine the force that pulls the sleigh forward, the force that tends to lift the sleigh. So the first thing that we're going to do here is if this is our sleigh and she's kind of pulling up like so, we have a force that she's pulling with, and that force is 200 newtons. We also know that this force can be broken up into its horizontal component, which we'll call F at x, or not F at x, but Fx, and the vertical force, which we'll call Fy. And despite my bad diagram, these do meet at a 90-degree angle. Also, we know that this is making an angle of 20 degrees with the horizontal. Okay, so very similarly to how we solved the last question, we're going to, for part A, find the horizontal force that tends to pull the sleigh forward by using our formula that we developed above. And that means that we're doing 200 times the cos of 20 degrees for this calculation. Okay, so I'm going to just approximate this. We'll round to one decimal place again. You should have here 187.9 newtons for the force that is pulling the sled forward. And then because she's not exactly pulling at a complete horizontal pull, she also is kind of lifting the sled a little bit, and that's going to be our vertical force, or the force in the y direction, which we'll calculate by doing the magnitude of the force times the sine of the angle that the sled is being pulled at. So entering this into our calculator, keep putting equal signs here, but these are more approximations. This is approximately equal to 68.4 newtons. For our final example, you may be familiar with questions like this if you've taken physics. So we're gonna look at a box that's weighing, obviously not weighting, weighing 140 newtons and is resting on a ramp that's inclined at an angle of 20 degrees. We're going to resolve the weight into the rectangular vector components that keep the box at rest. So let's take a look at our ramp here. We're going to draw a position diagram, and then we're going to translate that into a vector diagram, which will be a little bit more helpful to find the information we're looking for. Okay, when we're given weight, we're basically given the force of gravity. And in this case, that's 140 newtons. There's a couple other forces that are acting on the box here to keep this in a state of equilibrium. Remember, this says that it's resting on a ramp. So in order to keep this box at equilibrium, we know that the box wants to slide down because of the force of gravity. So we do have a force acting on this, which is basically parallel to the ramp. And this is the force of friction. So often we'll just refer to this as F. And we have one other force. And And we have a third force acting on this, which is essentially the force that a surface will exert on an object to prevent that object from basically falling through. So we have this perpendicular force to the object, which we call the normal force. Okay, so there's our three forces. Sometimes in physics, I know that you guys draw this normal force basically acting upward like this. So if that makes you happy, you can also draw that, as long as you know that the normal force and the force of friction meet at a 90-degree angle. Okay, so let's redraw this in terms of a vector diagram. Okay, so one thing that we do know, based on our previous examples, is that the force of gravity, in order for this to be in a state of equilibrium, the force of gravity needs to have an equilibrium vector that the normal vector and the force of friction add to in order to keep this box in a state of rest. Okay, so I've redrawn our ramp here, and I'm basically just going to kind of slide a couple things into a bit of a different position, just so I can show you a couple things as far as where certain angles come from. So here we go. We have the force of friction, which I'm just going to slide over here. We also have the normal force, which meets the force of friction at a 90-degree angle. Or sorry, the normal force. Hopefully I said that. And we have this force of gravity, which acts on the box, which has an equilibrium vector that adds to the normal force and the force of gravity. So the equilibrium vector is also going to be 140 newtons, but in the opposite direction. Okay, so here's kind of the cool thing here. If I know this is 90 degrees, and I know this little slice is 20, then we can create some information here. And that basically is that this, if I create just a horizontal line here, if this is 20, then this must be 70. And with our Z pattern, then I know this is 70 and this must be 20. Now that makes this resulting angle up here, if we just erase the things that we don't need anymore, that makes the resulting angle up here 70 degrees. Okay. So now we can find the force of friction and the normal force quite easily. We have two angles. It's a right angled triangle and we have one side. So let's just say we use 20 as our reference angle. You can also use 70. But because the ramp is at an angle of 20, I like to do it in terms of that inclined angle. So the normal force, or the magnitude of the normal force rather, is going to be equal to the magnitude of the force of gravity, or that magnitude of the equilibrium vector times the cos of the angle of the incline, which is 20. So we're just going to enter that into our calculator here. And that gives us approximately 131.6 newtons. And similarly, the magnitude of the force of friction is going to be equal to the magnitude of the force of gravity, or that equilibrium vector, times the sine of the incline. Okay, so I just wanted to explain to you guys exactly how we're getting these angles. Sorry, my cat is wanting to make a guest appearance in this video. So I guess we should put the approximation symbols here. And in the future, when you do questions like this, you can essentially just kind of jump to these points here where you use the force of gravity and the sine and cosine to find the normal force and the force of friction. So this gives us approximately 47.9 newtons for our force of friction.